Okay, so we are in Generalized Linear Models with examples in R, that book right there, and we're on question 3.2. Okay, so we are meant to consider the hat matrix H, and so hopefully you're familiar with the hat matrix. We won't really go into it here, but it's defined in the chapter, and we'll look at it here in a second. And we're meant to show that it's idempotent, that it's symmetric, and also that that I minus H is both idempotent and symmetric. So we'll kind of expand on some of these ideas as we go along. Okay, so part one, we want to show that H, and H is given down here, is idempotent. Okay, in other words, that if we multiply H by itself, we always get back H. Okay, so so just to kind of expand on this idea of what idempotent is, so it means that if we take something and we operate on that something with itself, we get itself back. So for example, the number 1 is idempotent under multiplication because 1 times itself is 1. Okay? And similarly, the identity matrix here, this is an example, this is a 2 by 2 identity matrix. If we multiply that by itself, we get itself again, right? So I times I equals I squared equals I. Okay? And so we're asked to check that the hat matrix, given here, and I'm simplifying it by getting rid of all of the subscripts, the W subscripts, we're asked to see if this is idempotent. Okay, so now remember, what is the hat matrix? If we multiply the hat matrix times y, we get our estimate for y. We get y hat. Okay, anyway, so here's our hat matrix. So I'm going to multiply it by itself. Okay, so here's the first hat matrix. Here's the second hat matrix right there. Okay, well, notice that when we combine them, we get xtx times x. So I can combine those here. Well, now we have xtx times the inverse of xtx. Okay, and so by rules that we're not showing here, xtx is a symmetric matrix. And when I take the inverse of a symmetric matrix, then I get the identity matrix right here. Okay? So now all of this has just been boiled down to this. Well, the identity matrix times anything is just that thing again. So if I take x transpose times I just get x transpose. So I can get rid of the I, and I have this. Well, that is the hat matrix, right? So we've shown that the hat matrix is idempotent. Okay? Next part is we're meant to show that the hat matrix is also symmetric. So in other words, if I take the transpose of H, I get H back. Okay, so what is symmetric? So I mean, that is it, but just to give an example, if I take this matrix right here and I transpose it, okay, well, if I transpose it, all I do is I keep the diagonal values the same, okay, and then I flip across that diagonal. So this B will go here and this B will go here, but since B and B are the same value, I just get the same value. So the transpose is equal to itself. Okay. So what about H? Okay, so here we have H, and so the transpose of H, first I'm just going to write like this. Okay, so it's just a hat matrix and all of that in parentheses transposed. Okay. Well, there's a few properties that we'll utilize here, and we'll utilize them as we go to them or as we use them. So I'll revert back to this little list here. But the first one, so if I take the transpose of H here, well, so when we have the transpose of some big matrix, it's matrix multiplication here. We can abstract that here. So I have two matrices, A times B, and I take the transpose. Well, to do that, I change the order of B and A, and then take the transpose, okay, of each. So up here, that means that this xt is going to go to the first part. This xtx inverse is going to be the second part, and then this x is going to be the last part, right? So this is going to go to the front. This is going to go to the back. And then I take the transpose of each of these. And so we see that here. So here's that first xt, and I take the transpose of it. And then I have that xtx inverse and its transpose, and then I have that initial x here, and I take its transpose, okay? And that's by that first property there. And now I can start to simplify some of this. So if I take the transpose of a transpose, I just get, you know, the initial thing, okay? So that's the second property, right? So if I have a matrix transpose and then I transpose that again, I just get back the initial matrix, okay? And then let's see, what's the next thing to do here? Yes. So so this matrix right here, okay? This matrix right here is symmetric, and when we take the transpose of a symmetric matrix, I'm not proving that this is symmetric, but it is, and you should, I think it maybe talks about this in the book, but this is symmetric, okay? And when we take the transpose of a symmetric matrix, we just get that matrix back. That's what it is to be, that's what it is to be symmetric, okay? So we have that. So that means that I can just get rid of that transpose, and now I have this, right? And then I have X transpose, and I have that. Well, this is just H. So we show that HT equals H, and therefore it's transposable. Okay? Now finally, we want to show that I minus H is idempotent and symmetric. Okay, so now what is I minus H? So again, if you go back to the book, I minus H is basically the residuals in a linear model. Okay. So, so first let's show that it's idempotent. We've already talked about idempotent matrices up here. So I just want to show that I minus H times I minus H equals I minus H. And so the way that we would do that, so we can kind of distribute the I and the H of this first one, right? So I times I, negative H times I, negative H times I, so on and so forth. I times negative H, okay? And so we get this, okay? Well, I times anything is just itself, so I times I is I, and I times H here and here is just H, so we can add those two H's together, those two negative H's together, okay? So now we're left with this. And now remember that H times H, well, because H is idempotent by what we already showed up here, well, then that simplifies to just H, okay? So now we have I minus 2H plus H. Well, that's I minus H, and so we've shown that it's idempotent, right? Because we took I minus H times itself, and we got I minus H. Okay? And now we want to show that it's symmetric. Okay? So here I have, I'm going to take the transpose of I minus H. Now earlier when we were multiplying these matrices by this right here, we had to change the order of the matrices. That was because we were matrix multiplying. But here we are subtracting the matrices, and so we don't change their order. So we just take that transpose sign inside, and we get I minus T, or I'm sorry, I transpose minus H transpose. Okay, but we've already shown for one that H is symmetric, so H transpose is the same as H. And then way up here in the beginning, we saw an example of an identity matrix, and you'll notice that it is symmetric, right? It is the same on both sides of the main diagonal there. So I transpose is just equal to I, and so we get I minus H. Therefore, I minus H is symmetric. Okay, that's it.